All right, let's dive in. We're going to talk about a world where things can be in two places at the same time, a world where just looking at something actually changes it, a world where everything you think is solid, well, it might not be. We're peeling back the curtain on the absolutely bizarre, mind-bending rules of quantum mechanics.
So let me ask you something. That chair you're sitting in, the light coming from your screen, it all feels pretty solid, pretty real, right? But what if? What if it's all just a kind of illusion? What if the real rules of the universe, the ones operating underneath everything, are completely different, almost magical? Because that's not a sci-fi movie plot. That's the rabbit hole physicists tumbled down about 100 years ago. Okay, so let's set the scene. It's the end of the 1800s. Physics is like on top of the world. Seriously, physicists were feeling good. They had Newton's laws for how things move, Maxwell's equations for light. They basically thought, yep, we've pretty much figured it all out. Just a few little details to tidy up. But there was this one tiny, nagging problem that was about to blow the whole thing wide open. And that problem had a seriously dramatic name, the ultraviolet catastrophe. See, according to all the physics they knew, any hot object, like a hot piece of metal, should have been pumping out an infinite amount of energy as ultraviolet light. I mean, a literal cosmic meltdown. But it wasn't happening. When they actually measured it, the energy went up, hit a peak, and then dropped off. Reality just wasn't playing by the rules. The physics they trusted, yeah, it was completely, totally broken. This is a great way to think about it. You know that crazy tesseract scene in Interstellar? That's what was happening. Classical physics was looking at reality like it was a straight line on a piece of paper. But the universe itself was playing in like a whole other dimension that they didn't even know existed. So what do you do when reality itself is broken? Well, a guy named Max Planck comes along with an idea. And this idea was so out there, so completely bonkers, that even he was sure it was just some kind of mathematical trick. But this little trick? It turned out to be the very first clue in this whole quantum mystery. Here's what he said. What if energy isn't smooth? What if it's not like water flowing from a faucet, but instead it comes in tiny individual little packets? He called them quanta. The analogy of pixels is perfect. A photo on your screen looks totally smooth, right? But if you get super close, you see it's just a bunch of tiny dots. Planck was saying, hey, maybe energy is just like that. Maybe it's pixelated. And the craziest part? This weird little trick of his? It worked. I mean, it worked perfectly. It solved the ultraviolet catastrophe just like that. He didn't even really mean to, but Max Planck had just stumbled upon the key and unlocked the door to quantum mechanics. And behind that door was a reality way, way stranger than anyone was ready for. Okay, so Planck gave us our first big clue. Energy comes in packets. But what does that mean for something like light? Well, enter the next detective on the scene, a young Albert Einstein. And he was about to take that clue and just blow this whole case wide open. He decided to tackle a question that people had argued about forever. Armed with this new quanta idea, he asked, okay, let's settle this. Is light a wave? And I mean, all signs pointed to yes, for sure. You do this classic experiment where you shine light through two tiny slits. You don't get two lines of light on the other side. Nope. You get this whole interference pattern, just like when you drop two pebbles in a pond and the ripples overlap. So light is obviously a wave. It spreads out, it interferes with itself. Easy. Case closed, right? Well, not so fast. Because Einstein then looked at something totally different, this thing called the photoelectric effect. And he asked the exact opposite question. And the answer was also yes. He realized that light can literally knock electrons off a piece of metal, like you're shooting tiny little cannonballs at it. And that only makes sense if light is made of tiny individual particles, what we now call photons. So, wait a minute. It's a wave and it's a particle? It's somehow both? This is what we call wave-particle duality, and it is a huge deal in the quantum world. The Doctor Strange analogy is honestly perfect for this. The same reality can look totally different depending on how you're looking at it. That's light. Ask it a wave question, you get a wave answer. Ask it a particle question, you get a particle answer. It's whatever you're looking for. Okay, so reality is already way weirder than we thought. But you might want to buckle up, because we're about to go from weird to I don't even know what's real anymore. Because it turns out the quantum world is, well, it's kind of camera shy. The simple act of observing it changes everything. And this leads us to maybe the weirdest idea of all, superposition. Superposition means that before you measure it, a particle is in every single possible state at once. It's a blur of pure potential. To show just how bizarre this is, a physicist named Schrödinger imagined putting a cat in a box. Its life depends on a random quantum event. The upshot? Until you open that box and look, the cat is not alive or dead. It is, somehow, in a state of being both alive and dead simultaneously. And this gets to the heart of what we call the observer effect. Watching isn't a passive activity here. Remember that double-slit experiment? Well, if you put a detector by the slits to see which one the electron goes through, poof, the wave pattern disappears. It just acts like a boring old particle again. The very act of measuring it forces reality to pick a side, to snap out of that blur of possibilities and collapse into just one single outcome. This analogy is just perfect. It really is the everything everywhere all at once of physics. A particle is exploring all possible universes, all possible paths at the same time. But the second you look, you force it to pick just one timeline, the one that we get to see. All right, we're heading into the deep end now. This is where the rules of reality don't just bend common sense, they shatter it. We're talking about things that seem to defy space and time itself. Get ready for some genuinely spooky action and a few ghostly tricks. First up, the Heisenberg uncertainty principle. And this is key. This isn't about having bad measuring tools. This is a fundamental rule of the game. It says there's a cosmic trade-off. The more you know exactly where a particle is, the less you can possibly know about where it's going. And vice versa. The more you know exactly where it's going, the less you know where it is right now. It's like reality itself has a built-in blurriness that you can never ever get rid of. Then we have what Einstein himself called, and he did not mean it as a compliment, spooky action at a distance. We're talking about quantum entanglement. Imagine you have two particles that are linked together like a cosmic pair of twins. Their fates are locked. If you measure one of them over here, you instantly know the state of its partner, even if that partner is millions of light years away. Instantly. Faster than the speed of light. It's a connection that, honestly, shouldn't be possible. And for our last trick, we have quantum tunneling. So, because particles are also these waves of possibility, there's a tiny but real chance that a particle can just appear on the other side of a wall it shouldn't be able to get through. It's literally like a ghost walking through a solid barrier. And this isn't just some weird theoretical idea. This is how the sun works. It's happening constantly. So there you have it. We've gone from the first tiny crack in old school physics to this whole new world run by chance, uncertainty, and spooky connections. But here's the thing.
We have only just scratched the surface.
Because in part 2, we are going deep. We're going to ask what actually counts as an observer. Does it have to be you or me, or can a rock do it? We're going to look at how that spooky action is being used right now to create things like unhackable communication. We'll find out where quantum tunneling is hiding inside the phone or computer you're using, and we're going to tackle the biggest question of all. What does it mean for us to live in a universe that is, at its core, uncertain? So yeah, we've seen how common sense physics just completely fell apart. We've cracked open the door to this bizarre new reality, but we haven't really walked through it yet. Next time, we're going all the way in. And if you think it can't possibly get any weirder than half-dead cats and particles that walk through walls, trust me, you haven't seen anything yet. I'll see you in part 2.